Hello, good afternoon. So this is our lecture 2 of the data structure course, where we're just going to talk about the abstract data types and object orientation. So let's get started. Now the first thing that I wanted to talk about here, and I'm back to page 1 again. Let me see. All right. So I wanted to talk about abstract data types, ADTs. So what are those? They're just conceptual models or mathematical models. So they don't really exist. Okay, like mathematicians, they don't exist, right? It's just like that. These conceptual models, they just tell you what the data type is about and what are the operations you can perform on them. So two things that make up any ADT. There are two things. One is the abstract data structure, and then we got the operations that you can perform on those data structures. And this is where it gets interesting, because everything still stays abstract. And I want to start off with an example, because I think it makes more sense that way. Okay. So, for example, let us take up this thing called rational number. Okay. Now, rational numbers, they have two parts. One is called the numerator. The other thing is called the denominator. And if this doesn't ring any bell, rational numbers, mathematically, what you call these things are any numbers that can be represented in P by Q form, where P and Q, they're two integers. Or in other words, just call them fractions. I think it's so much easier that way. So just to give you an example, 1 by 3, that's a rational number. And 2 by 5, that's also another rational number. Now this thing, if you want to represent that as a floating point number or a number with a dot, it's never going to end. You have 0.333333, and it goes on like that. It is still a rational number. It cannot be confused with something which is not a rational number. So for example, pi is not a rational number because you just cannot write it in in P by Q form. So if you want to represent pi as 22 by 7, then this is definitely going to be wrong, right? It's a very bad approximation of pi, and that's why, well, you just cannot find two integers which you can write a ratio of to represent pi. And for 1 by 3, you can say that if you write it as 0.333, this is incorrect. If you write it as 0.3333, then it's a little bit better, but it's still not correct, right? The important thing about rational numbers is that it can be represented in P by Q form. And that's the only thing that you got to be bothered about. So for these rational numbers, let's just take two rational numbers as example. Let's say we got a equal to 1 by 3 and we got b equal to 1 by 5. There are a lot of operations that you can perform on them. So for example, you can say that c is equal to a plus b, where you're going to perform the addition operation. And the way we do this, is going to be 1 by 3 plus 2 by 5, like this. And then you carry out the operation as such that you calculate the least common multiplicand at the bottom for the denominator, or you just carry on the multiplication without even thinking about LCM. In this particular example, they're both the same. So 3 times 5, that's 15, and then you have 5 here, and you got 3 times 2, which is 6. which results in 11 divided by 15, and that's the answer. That's equal to 11 by 15, which again is another rational number. So for ADTs, when you talk about the ADTs, what you got in here is that you have the abstract data structure where we just say that there are two things that you need for rational numbers. You need to store the numerator and the denominator. Okay, and for the operations for this particular mathematical model, and this example is just from math, right, pure math, and for operations you can say that given two rational numbers you can carry out an add operation or a subtract operation or a multiply operation, and then a divide operation. What else? For a rational number, maybe we want to define another operation like you got 16 divided by 12, which you can reduce further. You can divide both these numbers by 4. So 4 4s are 16 and 4 3s are 12. So you can write the same number as 4 by 3, which is kind of like a reduction operation. So in terms of the operations we can define, let me just add one more here. Just to spice it up, to give it a little bit of a different flavor, we got 5 different operations we can perform on this particular example, which is our rational number, right? And if you look at this definition right here, where we are creating this abstract data type, we are calling this, the abstract data type is called a rational number. We know this rational number as something that has two things. The data structure consists of the numerator and the denominator. And for the operations, we got add, subtract, multiply, divide, and reduce. And that's pretty much it. So that defines our abstract data type. And the reason why we are talking about abstract data types here is because when we look at the data structures, the ones that we are going to learn, it's going to be pretty much the same thing. We will cover this later on, but let me bring this up. Some of you may know about this already from your computer fundamental course or some of the course that you may have had studied. Okay, we talk a lot about this data structure called stack, which is pretty much a last in, first out data structure. And to give you a real life example, when you go to any party, if you think about the plates that get served on a table and then people eat and then they leave it off. So all these plates, they need to be washed, right? They're taken to the sink to be washed. And when they're taken to the sink, let's say this is a plate and it's a really bad drawing. This is another plate and this is another plate. And let's say we got 4 plates like this. When someone's going to go and wash them, right, under a sink, are they going to take out the very last one? Because this is the one that got left in there right at the beginning? No need, right? So we are going to take the first plate off from there. We are going to wash it under the tap and then put it in a clean pile, and then we're going to pick the next one. So if you look at the stack data structure, this was a real life example. The question that when we talk about the ADTs, how do you represent stack as an ADT? We will think about the underlying data structure that represents a stack, and we will say what are the operations that can be performed on a stack. So stack can be represented in so many different ways, and one of them is just by using an array. That says that the underlying data structure is an array, and we also need to maintain the top index that tells you what's the last element, where was the last element that got inserted in that stack. So this is the abstract data structure we are defining, but in terms of the operations that you can perform on a stack, those can be like push, where you push a plate. I mean, since we are talking about that real life example, you can push down a plate, or you can pop off a plate. You can take it off, right? So push and pop, these are the two fundamental operations that you can perform on a stack. And this is not just these two. You can also have another operation which is called isEmpty. It's a query operation. It's like asking the stack whether the stack is totally empty or not. Yeah, it's a yes/no answer that you're going to get. So with these three operations, you can implement a stack, although most times you also have another operation here, which is called pick, which lets you look at the topmost element of the stack. Now, before going on to the stack, which is going to be a pure data structure topic, let us play around with this toy data structure that we got as a conceptual model as an ADT. We're talking about the rational number as an example, and we have defined this ADT so far. So defining the ADT is really very simple. You just name the data structures, what are the things you're going to store. So let me write that down. The data structure is about what are the things you can store, and I cannot spell store. Now I can. All right, what are those items that you are going to store, and what are the things you can do? All right, things you store and things you can do. So things you can do, they define the operations, and things you store, they define the abstract data structure. Altogether, these two things, they define the ADT. So that's pretty much it. Okay. But if you think about the ADT, it's just a mathematical model. It doesn't really exist in real life. You still need it. That gives you a basic idea which you can flesh out, and that's what we are going to do. We will take this idea of a rational number and we will take it to the next level. We will create a data type out of it in our language. Okay, and before we even get there, we'll take this idea into something called a class diagram, and that's where object orientation comes into play, because this is all going to be about the stuff that you have, your data, and what are the things that you can do on your data. We will create a data type out of it, which you can then translate into any of the programming languages we got, like any of the object-oriented programming languages we got. It can be C++, it can be Java, or it can be anything really. So yeah, we will get there. We will take this into a design first, which is still not going to be a program, okay? But that gives us a basis of writing a program right from there. So I'll stop recording this session, and then we'll be right back where we are going to design this data type in terms of something called a class.